So you can follow along either in your notebook or you can print out the PDF attached here to Schoology and follow along by copying your notes into the document themselves. If you want some extra information, you can go to page 194 to 204 of the Princeton Review book. This video is meant to be a summary of chemical kinetics, or the speeds of chemical reactions. It's important to know that we've already talked about this a little bit in equilibrium, in that equilibrium represents equal rates between the forward and the reverse reaction. This is also meant to introduce you to a little bit more content, so when you get back, we can jump right into specifically how concentration affects equilibrium. Very important. So I need you to watch this video, fill out the form before we get back after spring break, and follow along in your notes. So let's do a little remembrance of collision theory. So in order for a reaction to occur, reactant molecules must collide with two things. First, they must collide in the proper orientation, okay? And secondly, they must hit each other with enough energy to overcome that energy barrier. And when we say enough energy, we're really referring to the activation energy, or the E sub A. Now we can affect the orientation or the energy in four primary ways. And the first is by changing the average kinetic energy of the particles, or the temperature. So if we had a reaction going from A to B and we plotted energy here and just the reaction happening in the forward direction here, we'll make this an exothermic reaction because it ends lower. That activation energy is this hill. And temperature does not change that hill. Temperature simply gives you the energy needed to get to the top of that hill. Okay. Now, if you look at all the reactions in a Maxwell-Boltzmann distribution, and we put energy here, and we put the probability of the particles having a specific energy here, we get a normal distribution, where that activation energy is now on the x-axis. These reactants have collided with enough energy in the correct orientation. Now this is the average temperature, so if temperature increased, the graph would shift this way, getting lower, but also giving more particles more activation energy. A decrease in temp would look like this. Now it's a little counterintuitive, but it's really the shaded region past the energy of activation that matters. This is the higher temperature, that's the lower temperature. Now, if we change the concentration, I put temperature twice here, that's stupid. If we change the concentration by adding more solute particles or taking away of some of the solvent, or conversely, taking away solute particles or adding more solvent, we are going to get more or less successful collisions, but not because we're changing the temperature. So, again, the energy diagram is not going to change. It's still going to require a certain amount of energy for A to go to B. That energy we call the energy of activation. What is going to change, again, is the Maxwell-Boltzmann distribution, where we have this normal distribution and we have the energy required for a reaction to happen successfully. But unlike the temperature value, the average temperature is not going to change. All that's going to happen is an increase in the relative size of the curve, allowing more particles to react, because simply there's a greater opportunity for them to collide with the correct orientation. So concentration and surface area, they're really concerned with the orientation. Temperature, energy. And there's a question like that on your multiple choice quiz. Now, a catalyst is a much different phenomenon. A catalyst is the only one that actually changes both the Maxwell-Boltzmann distribution and the energy diagram. So the energy diagram for a catalyst looks like this. And by the way, surface area and concentration have the same effect, because essentially by grinding something up, you're exposing more particles to collide with the correct orientation. That's analogous to actually just adding more particles. In a catalyst, what it's going to do is it's going to provide a new reaction pathway. We'll talk more about that after break. That requires a little bit less energy, and that's the catalyzed pathway. You start and you end at the same spot. So because we actually have a new EA, the shape of the Maxwell-Boltzmann distribution is not going to change, but the location of the activation energy will. Looping in more total particles there. Okay. So if you notice, all of these loop in more particles. Temperature by actually shifting it to the right, concentration or surface area by actually shifting it up, and the catalyst by actually shifting the location of the EA. Notice that the catalyst is the only one that changes the EA. The only one. That's a really important thing to understand. Okay. So what we're going to do now is introduce something new, and I'm telling you right now, this is very, very simple and very, very intuitive. We are going to focus on the effect of concentration only. Okay. And here's how we're going to do it. Okay. So concentration, remember, is moles per liter, or big M. And that's called molarity, and that's going to show up here in a little bit. Okay, so intuitively we know that increasing the concentration is going to increase the probability that they're going to collide with the correct orientation. It's not going to increase the energy. Okay, but the story doesn't end there. It turns out that changing the concentration of reactants can actually change the concentration or the rate differently depending on the shape and the behavior of those reactants. Okay, you can think about it in biochemistry. That enzyme-substrate relationship is affected by the way they bind together. Okay, so it's not always a simple one-to-one relationship. So the concentration effect. First off, changing the concentration of a reactant can change the rate differently. And the way it changes the rate differently, we call the rate order. And we talk about three primary rate orders. We talk about a zero order, we talk about a first order, and we talk about a second order. Okay? In zero order, the rate is not affected by changing concentration. Okay? In first order, the rate is affected in a one-to-one manner by changing concentration. And in a second order, the rate is affected by the power of 2 in an exponential fashion. For example, if you double the rate in a zero order situation, nothing would happen to the rate. In a first order situation, if you doubled the rate would also double, 1 to 1. Okay? And in a second order situation, if you doubled the rate or doubled the concentration, the rate would triple. So let's look at a reaction. A goes to B. Okay. In a zero order fashion, we can say that the rate is equal to A to the 0 power. What that means is the rate is not affected by A. No matter what you put in for A, that's always going to default to 1. And we can put this little lowercase k, we'll call that the rate constant. In a first order situation, we can say that the rate is equal to the rate constant. Really, the rate constant determines the speed of the reaction when you're not changing anything. A to the first. So what this means is that if you double A, the rate will also double. If you triple A, the rate will also triple. If you have A, the rate will also have, because of that 1 there, first order. And I'm sure you can guess here, second order would say that the rate is equal to the rate constant. Think of that as the slope of the line. Now this is a little k. It's not K-E-Q. It's a little teeny k. Hi k, you're so little. Times A to the second. So if I double A, this would quadruple. If I triple A, this would increase by a factor of 9. Okay? If I quadruple A, this would increase by a factor of 16. That's called second order. So reactants to our second order have a much greater effect on the reaction. Reactants that are zero order have no effect on the reaction. And this is really a counterintuitive thing. Now notice A here is just a chemical. This could be hydrogen peroxide, water. So what's going to go in these brackets will change. It's also important to remember that brackets refer to molarity. So let's look at an example problem. Okay. So we have this example reaction. A plus 2B plus C goes to D. First off, the coefficients here are not always the orders. Sometimes they are. Meaning, this does not mean that A affects the rate of the reaction in a first order fashion. This does not mean that B affects the rate of the reaction in a second order fashion. And this does not mean that C affects the rate of the reaction in a first order fashion. What we have to do is an experiment. So let me show you what they did in this experiment. In this experiment, they did 4 different experiments. Okay? In the first experiment, they had the rate measured when the concentration of A was 0.1, B was 0.1, and C was 0.1. They measured the rate of the reaction. In the second experiment, they held A and B constants at 0.1 and just changed C and looked at what happened to the rate of the reaction. In the third experiment, they held A and C constants and just changed B and looked at what happened to the rate of the reaction. And in the fourth, compared to the third, they held B and C constants and just changed A and looked at what happened to the rate of the reaction. So by doing this reaction 4 times at different concentrations, we are able to see the way A and B affect the rate. So here's how you go through and find the orders. Remember, the orders are going to be either 0, 1, or 2. 0, A, B, or C would have no effect on the rate of the reaction. 1, A, B, or C would have a direct effect on the rate of the reaction. Double, double, triple, triple, half, half, quadruple, quadruple. C, A, B, or C would have a power of 2, an exponential effect. That is to say that double, quadruple, quadruple, 16, 3, 9, half, 4, etc. So here's how you do it. In order to get the rate order for A, we have to find where B and C are constant and A changes. So let's find A. If you look at 3 and 4, A changes and B and C were both held constant. So that's going to allow us to see how A affects the rate. So the way I do it is I just divide 3 over 4. So what I'm going to do is I'm going to take A, concentration at A at 3 over 4, and I'm going to set that equal to the rate of 3 over 4. So A is 0.1, 0.20. And the rate is 0.02 and 0.08. Okay? And I'm going to put X here, and that's going to be the order. So when I reduce it down, I get 0.5 to the X equals 0.25. So then I try 0, 1, and 2. So if I put in 0 here, that would be 1. So it's not 0 order. If I put in 1 here, that would be 0.5. So it's not first order. If I put in a 2 here, that would be 0.5. So A is second order. Meaning A affects the rate. Now this is cool because if you notice the coefficient here is 1, but it's actually second order. So there's something more complex happening. So let's go down to B. If we want to study B, it's going to be the same situation. We need to find 2 reactions where B changes and A and C do not. So let's look here. By comparing 1 and 3, B goes from 0.1 to 0.2. So if you look at B goes from 0.10 to 0.20, and everybody else stays constant. Okay, so A does not change and C does not change. Therefore, we can look at the direct effect of B on the rate, its concentration. So the rate goes from 0.1 to 0.2, 0.01 to 0.02. So if we reduce that down, we have 0.5x equals 0.5. So if we plug in a 0, that would be 1. So it's not 0 order. If we plug in a 1, that would be 0.5. So we know that this is first order. Okay? And now let's do the final thing with C. Okay, so again, for C, we need to find a place where C changes, but A and B do not. If you look at 1 over 2, C changes, A and B do not. Therefore, we can find the effect of C. So the concentration of C goes from 0.10 to 0.20 x equals the rate. The rate goes from 0.01 to 0.01. So this is 0.5x equals 1. So let's plug it in. If you plug in 0, 1. Okay, so it's 0 order. Okay. So once we find all the orders, we write the overall rate law equation. It's kind of like an y equals mx plus b equation. It expresses the way that the rate of this reaction here is affected by changing A, B, and C independently. So the rate law is always equal to little k. So little k is the rate of the reaction when you don't change anything. We call that the rate constant. And then you take A, you raise it to the second power because it's second order. You take B, you raise it to the first power because that's first order. And you can take C and raise it to the 0 power, but we don't need to put it in there. So the rate expression is rate equals K, or the rate law equation is rate equals K to the second power because it's second order, and B to the first power because it's first order. The overall order for this reaction is simply the sum of these things, and that's 3. So if you change them both simultaneously, it will increase by a factor of 3. Now, to get the value of the rate constant expression, it's really easy. All we have to do now is pick any one of these experiments and plug them in. Okay, so let's just pick experiment 1. So at experiment 1, the rate is 0.01. Okay, we're trying to solve for K. A is 0.10 squared, and B is 0.10, and we don't have to put anything in for C because it's simply not there. It's to the 0 power, it doesn't affect it. So K, if we rearrange this, is equal to 0.01 divided by 0.10 squared multiplied by 0.10. Now, some people might be able to, and we can solve for K, and you're going to get a number, and there's units on K that we're going to learn a trick for when we get back. Okay, so just beware of that. Now, some people can intuitively look at this, and they can intuitively, without doing all this crazy math, say, all right, if I want to find A, I need to find a place where A changes and everybody else stays the same. That's 3 and 4. So they can say when A is doubled, the rate is quadrupled. So they can say, boom, A is second order. Then people can say, man, for B, I need to find a place where A and C are held constant and B changes. Okay, that's 1 and 3. So A doesn't change, C doesn't change. B's doubled, the rate's doubled. Boom, B's 1. And then they say for C, I need to find a place where C changes, but no one else does. Okay, so that's 1 and 2. So C's doubled, no one else changes, and the rate does not change. So I know, boom, that's 0. So some people might be able to do that. So I'd like to challenge you guys to look at this question from 2008 and try and solve it. Now, instead of A and B, we have NO, that would be like A, and O2, that would be like B. Okay? So this reaction, what they're going to ask you to do is find the orders. Is NO 0, 1, or 2? And is O2 0, 1, or 2? Then they want you to write the expression, that's the rate equals K, NO to some power, O2 to some power. And then they want you to find the value of the rate constant K by simply plugging one of the experiments in. I always choose 1. Don't worry about the units until we get back. So in order to find this answer, what I encourage you guys to do is Google the 2008 AP Chemistry Free Response Scoring Guidelines. And you'll be able to find the answer. Okay. Is that still scoring? Yeah. When we come back, I'd like you to have all of this in your notes, fill out the form below, and we're going to work on some problems like this. You can do it the math way or not the math way. But remember, concentration can or cannot affect the rate. And the way it does is called order.